in the industry at places such as Microsoft Research and Nokia Bell Labs. And he is currently on the job market and he welcomes any potential opportunities for him. So thanks, Desik, for joining us and agreeing to talk about your work. And we are excited to hear more. You can go ahead and start sharing and presenting.
Yeah. Can you see my screen?
Yes, it's good.
Yeah. So hi, everyone, and thank you very much for the very kind introduction, Nitin. I'm Desik, and I'll be talking about enhancing reinforcement learning using data and structure in this talk. Before we start, I'd like to just give a brief overview of what reinforcement learning is, because at least in the poll, I noticed that a lot of folks are pretty new to reinforcement learning. And in reinforcement learning generally consists of a learning agent and an environment where the learning agent interacts with the environment. So the environment gives a state and the learning agent looks at the state and takes an action. And this action essentially changes the state of the environment and gives the learning agent some sort of reward. And this process continues over and over again. An example of this would be, suppose we take the case of autonomous driving. Your environment can be like your car. And the state of the car can be its current position, some camera, the current view, what it sees, or some LiDAR data, and so on. A learning agent can be a neural network or any other sort of algorithm which can basically use the state information to generate actions. And your action can be your driving control, such as your steering inputs and your acceleration and throttle. Right? And the goal of reinforcement learning is how do you learn the optimal sequence of actions in an unknown and evolving environment, because the learning agent does not really know how the environment works, and it has to learn how the environment works by interacting with it. And at the same time, the environment evolves as the agent starts taking actions in it. So the goal of the agent is to learn in this unknown and evolving environment the optimal sequence of action that it must take in order to achieve, in order to maximize some long-term reward. So that's like a brief overview of what reinforcement learning is, and I'll go ahead into details as the talk progresses. Reinforcement learning in the recent past has seen quite a lot of success. Like, for example, in 2015, we had DeepMind come up with playing deep Q learning for Atari games, which was really popular. And then later in at least till 2017, DeepMind again came up with AlphaGo, which beat like players in the game of Go and chess and so on. And more recently, Sony AI came up with this agent to play Gran Turismo, which I think in Gran Turismo 7, you'll have agents who are trained using reinforcement learning competing with players. And again, DeepMind has come up with reinforcement learning for figuring out new ways of doing matrix multiplication. And Google came up with reinforcement learning for chip placement, and recommendation systems have used reinforcement learning in places like Netflix, Microsoft, and Yahoo over the past couple of years. So reinforcement learning algorithms have been pretty successful in these scenarios, and this has mainly been limited to some structured or very simulated environments. And the success of reinforcement learning algorithms in the real world is pretty limited. That is, they're not any wide-scale real-world deployments of reinforcement learning algorithms. And this is mainly due to some challenges that reinforcement learning algorithms face. Right? So some of the challenges that reinforcement learning algorithms face are as follows. One of them is essentially the idea of designing reward functions and learning in sparse reward environments, because your reward functions kind of tell you on what the actual task you want your agent to solve. And hence, designing these reward functions is actually a very hard problem, which I'll talk about in this talk. And second is that reinforcement learning algorithms generally require a large number of samples during training, which is hard to collect in many real-world scenarios. And third, adapting to new environments for reinforcement learning algorithms is very hard, because if they have trained on one particular environment, and if you have to adapt to a new environment, you might have to retrain your algorithm all over again. And these are some of the challenges which they face, and there are many more. So in this talk, what I'll be doing is as follows. So I'll be talking about developing new reinforcement learning algorithms that make use of some side information. And this side information is used to basically enhance the learning procedure. That is, how do you make reinforcement learning algorithms better when you have access to some sort of side information? And in specific, I'll be talking about developing reinforcement learning algorithms that, one, learn in sparse reward environments using some sort of data for guidance. And this is one of the works which was published in ICLR in 2022. And second, I'll also be talking about reinforcement learning algorithms that exploit some sort of structural similarity among environments and then use data to learn in sparse reward environments. And I'll go into these details as the talk progresses. So before I move on, I'd like to start off with some reinforcement learning basics, and that starts off with modeling reinforcement learning using something known as the Markov decision process. So a Markov decision process is denoted by a tuple where S or script S denotes the set of states. These are the set of states which your agent can be in. And a script A denotes the set of actions that the agent can take. The transition kernel P essentially denotes the probability of transitioning to a state S dash by taking action A in state S. And the reward function is a function of the current state and action, which essentially tells us what's the reward you get for taking a certain action in a particular state. And for example, the way a reinforcement learning trajectory progresses is that you start off with some initial state S0, you take an action A, and then you get some reward. And this action essentially causes your state to change. So you move to another state S1, and then you take an action A1, you get a reward, and this process continues. So what is a policy in reinforcement learning? So policy is something which you'll be coming across multiple times. So policy is some sort of a rule book which an agent follows, which essentially maps your state to a distribution over actions. So a policy essentially tells you what action you have to take at a particular state. And what is the goal of reinforcement learning? The goal of reinforcement learning is to essentially find out a policy that maximizes the infinite horizon discounted reward. Essentially, suppose you start at a given state, for example. Suppose, let's say you start at state S0. What are the sequence of actions that you must take such that you maximize your cumulative sum of reward? Right? Or discounted cumulative sum of reward, where gamma is called the discount factor. So the discount factor essentially tells you that you care about rewards that come later stage lesser when compared to rewards you get currently. So the value function of a policy pi is essentially, of a policy pi at state S is essentially the reward you get starting from state S and following policy pi throughout. And the action value function, or the Q function, is essentially the reward you get when you start at a state S and take action A and follow the policy pi after that. So what is the cumulative sum of reward you get is known as the Q function. So the advantage function is something which we'd be using in reinforcement learning constantly. So the advantage function essentially tells you what's the advantage of taking action A in state S. So it's essentially the difference between the Q function as well as the value function. And another term that we'll be using constantly throughout this presentation is something known as the discounted state visitation frequency, which basically tells you that suppose an agent executes policy pi in an environment, what are the distribution of states it visits? So now we move on to like the basic problem that I'm trying to solve. And the problem that we're trying to address is that designing reward functions is a challenging problem in reinforcement learning. So why is that so? So reward functions are something which kind of tell you the task that you're trying to solve, and they kind of encapsulate what you want your agent to do, right? And if the reward function is not designed properly, what happens is that the agent will try to optimize something else and you won't get the desired result that you want. For example, I think over the past few days, like Nitin has been working on trying to design reward functions for a simple obstacle avoidance problem. And what happens is that if the reward function is not designed correctly, the agent just stays at a single position and does not move, because it feels that colliding with an obstacle is so bad that it doesn't even want to start moving. So you might get these undesired results if the reward functions are not designed well. What is intuitive is that it is intuitive to design sparse rewards. So what does this mean? It's easier to design rewards which just indicate whether a task is completed partially or fully. Like, for example, it is easier to say that your agent gets a reward of +1 if it reaches the goal, 0 if it doesn't reach the goal, and -1 if it collides for like a navigation problem. So for example, in indoor navigation, it's easier to provide rewards for either the full completion or partial completion of tasks. But what happens is that when you start providing sparse rewards to reinforcement learning algorithms, they fail to learn in a reasonable amount of time. Because if you understand what happens is that in reinforcement learning, the agent tries to interact with the system, get rewards, and then tries to maximize that reward. But when you're interacting with the system that does not provide you any feedback, then you're just basically getting no feedback on the actions that you take. So essentially, your learning doesn't happen. So here is an example of a simple environment on in the OpenAI gym setting, where when you provide sparse rewards, the agent fails to learn, while in the dense scenario, it learns pretty well. So the problem that we're trying to address is that how do we solve the problem of sparsity in reinforcement learning? In many problems, we have access to demonstration data, which might be collected by some behavior policy. So what do I mean by this? So for example, you might have problems where you have demonstration data which are collected by humans or by some empirical policy. For example, in indoor navigation or in some autonomous vehicle problems, you might have a lot of driving data which has been collected, or in terms of network problems, you might have data collected from some empirical policy. So this data might tell you on how to solve a task, but it might not be the optimal way to solve that particular task. So you might have access to some suboptimal demonstration data. Further, this demonstration data might also be incomplete in the sense that it might not contain measurements of all the states that you need, but it might only contain measurements of a subset of states. And I'll dwell into this idea of like demonstrations being incomplete further in the talk. But the idea is that in many situations, you might have access to some demonstration data, which kind of tell you how to solve a particular task, but it might be suboptimal. So the idea is that can we use such demonstration data to aid learning in sparse reward environments? And that's the problem that we're trying to address. And you must understand that like purely imitating this demonstration data is not going to work because this demonstration data is suboptimal. Second, just performing reinforcement learning in this environment is not going to work because you have sparse rewards. So what we do in this work is that we propose a principled approach to utilize the suboptimal demonstration data to learn in sparse reward environments. I hope the problem setting is clear. The problem setting is that reinforcement learning in sparse reward environments is hard. And suppose you have access to some suboptimal demonstration data, which kind of tell you how to solve that particular task. Can you use the suboptimal demonstration data to aid reinforcement learning? So that's the question that we're trying to answer. So what is the problem framework that we're trying to, that we put here? We want to develop an algorithm that uses offline demonstration data for reinforcement learning in a sparse reward environment. So we assume that the algorithm has access to demonstration data collected using some behavior policy, where a behavior policy is basically a rule which maps some states to an action, right? We assume that we either have access to the behavior policy or we have access to the data collected by the behavior policy. So D here denotes some end trajectories collected by a behavior policy, where a trajectory is essentially just state, action, state, action, obtained by executing the policy in the environment. So we need this behavior data to actually help learning. So we make some assumption on what the behavior data looks like. So the assumption that we make is that in the initial episodes of learning, the advantage with respect to actions taken by the behavior policy of the policy at iteration k is lower bounded by some value beta. So what does this essentially mean? It means that taking action according to the behavior policy provides a higher advantage or benefit than taking actions according to pi k. So what does this intuitively mean? So we need this demonstration data to help aid the learning process, right? And in order for us to characterize the idea of demonstration data help aiding the learning process, we need to assume that the demonstration data is actually better than the policy that is being used to learn in the initial stages of learning. And that's basically made concrete in this assumption. And this is done for like a theoretical, this is done to essentially show that our algorithm works in theory. So what is our algorithm? So our algorithm is known as LOGO, or Learning Online with Guidance Offline, and it consists of 2 steps. The first step of algorithm is known as the policy improvement step, which consists of 1 step of policy improvement performed using the trust region policy optimization algorithm, or TRPO algorithm, where TRPO is this popular reinforcement learning algorithm, which is used for policy learning. So what does TRPO do? The TRPO basically tries to find out a policy by maximizing the environment rewards. But we should understand that since the environment rewards are sparse, the step 1 might not actually yield any good results. So what we do is that we augment the step 1 with a step 2, which is known as the policy guidance step, where the policy guidance step essentially tries to find a policy which is close to the behavior policy or the demonstration data or the demonstration data that we have. But what we do is that we do not just want to find this behavior policy, but we want to find this behavior policy in a small trust region around the policy generated in the first step, right? So basically what we're trying to do is that each step of our algorithm has 2 parts. The first part is known as the policy improvement step, where we improve using the rewards obtained from the environment. And the second part is the policy guidance step, where we kind of change the policy suggested by improving the environment rewards using the demonstration data that we have. So essentially what this does is that the policy guidance step ensures that the policy chosen is guided by the behavior policy and we're not completely imitating the behavior policy. And this is done because the behavior policy might be suboptimal. So I'll dwell into each of these steps in more detail, and please feel free to stop me if you have any questions during the presentation. So the policy improvement step consists of 1 step of policy improvement using TRP, or the Trust Region Policy Optimization Algorithm, where we want to maximize the advantage of policy pi-k from states drawn according to policy pi-k and actions taken according to policy pi. So we want to maximize this over policy pi, subject to a trust region condition where d pi k KL is basically the average KL divergence between policy pi and policy pi k. So what we're essentially doing is that we want to maximize the advantage in a small trust region of around pi k. Doing only this will fail in sparse reward environments because TRPO fails to provide any reasonable improvement because of the sparse reward structure. Because what happens is that in order to compute this advantage pi k, you use rewards sampled from the environment, and if the rewards sampled from the environment are sparse, this will essentially be zero. So essentially, you're not really maximizing over anything, and your gradients will essentially be 0, so your policies are not going to change. So in order to overcome this challenge, we essentially use the policy guidance step, where we use the policy guidance step after every step of policy improvement to essentially guide the policy towards the behavior policy. So what does the policy guidance step look like? So the goal of the policy guidance step is to basically find a policy close to the behavior policy. So you want to find a policy pi that is close to the behavior policy. So you want to minimize the scale term. But you just do not want to do this directly, but you want to do this in a trust region around the policy suggested in the first step. So suppose in the first step, you get policy pi k plus half. You want to ensure that around the trust region of this policy, you want to find a new policy pi. So what this essentially does is that the trust region basically controls the amount of guidance we want the behavior data to provide. Right? So in practice, what we do is that we start with a large value of delta k. And as we move forward in our algorithm, we kind of gradually decay the value of delta k using an adaptive rule. So this ensures that we do not mimic the behavior policy directly, but only use it as a guidance around the policy suggested in the first step. So just to track back, so our algorithm has 2 steps. The first step is another policy improvement step, and the second one is another policy guidance step. So the policy improvement step basically improves over the rewards got in the environment, but in sparse reward environments, this might not be enough. So what you do is that you use the demonstration data to guide the policy towards the behavior policy. But going towards the behavior policy is going to be bad because the behavior policy might be suboptimal, and hence you want to decay this influence as you go ahead in training. So this diagram kind of summarizes what our algorithm does. So I'll go over this diagram because this will kind of explain the intuition with which we work with our algorithm, right? So suppose we start at some iteration. Suppose we have our policy pi k, right? So first we do a policy improvement step, right? So this policy improvement step is done using the rewards from the environment. What happens is that because of the sparsity of the environment, this policy improvement may not be in the direction of the optimal policy. So here pi star is our optimal policy, and pi b is the behavior policy, or the policy that generated the demonstration data, right? So the policy improvement may not be in the direction of the optimal policy because of sparse rewards. Then what we do is that we use, we basically do the policy guidance step in a trust ball around the policy suggested by the policy improvement step. So we take pi k plus half, and then we consider a ball around pi k plus half and try to find a policy pi k plus 1, which is directed towards the behavior policy. And we do this over and over again. And then as we go ahead in our learning process, we do not want to end up at pi b. We do not want our algorithm to end up at pi b because pi b is suboptimal. So what we do is that to reach the optimal policy, we decay the behavior of we decay the influence of the behavior policy, right? So this ensures that after a few steps of training, we start moving in the direction of the policy, in the direction of the optimal policy. So this is kind of like the summary of our algorithm. So what are the theoretical guarantees that we can provide for this algorithm? So we show that suppose pi k and pi k plus half are related by the policy improvement step, and pi k plus half and pi k plus 1 are related by the policy guidance step, then we show that if pi k plus half satisfies our assumption, that the assumption being that the behavior policy provides you some benefit during the initial stages of learning, then we show that the performance improvement of our policy. So what is the performance improvement? It's the difference between the performance of the policy pi k plus 1 and the performance of policy pi k. So the difference is lower bounded by the following terms. So the first term is essentially the improvement due to the policy improvement step. And the second term is the improvement due to the policy guidance step. And note that the improvement due to the policy guidance step has two terms. The first term being the advantage due to the behavior policy, and the second term being the distance to the behavior policy. So if you notice that our algorithm essentially tries to, maximize this lower bound, right? So because we minimize the distance between pi k plus 1 and pi b in our policy guidance step, they're essentially maximizing this lower bound. And this policy improvement is also obtained by maximizing the policy improvement step objective. So this kind of provides like a sanity check saying that, yes, our algorithm will provide us a monotone policy improvement. So what happens if we do not satisfy the assumption? Suppose we do not satisfy the assumption that the behavior data is actually providing us any improvement. And this happens in our algorithm because at some point your behavior data might not give you any improvement over your policy, and you must use the rewards from the environment to learn better. So in that case, we show that the policy improvement is lower bounded by two terms. The first term is essentially the improvement due to the policy improvement step. And the second term is this term, which essentially hampers our policy improvement because it consists of this R max here. But we notice that we have a delta K that creeps in here, which essentially means that as we move forward in our learning procedure, we must decay this delta K to prevent our policy guidance step from hampering the learning process. So both of these things basically tie in well with the way our algorithm works, saying that we can provide policy improvement even when our assumption is not satisfied, and that's achieved by decaying the value of delta K. So I can pause for questions if there are any, but I can just summarize as to like what we have done till now, just to get a hand of where we are. Right. So where are we? So I initially mentioned that like learning in sparse rewards is challenging in learning in sparse rewards environment is a challenging problem for reinforcement learning. And we basically described our algorithm, which is known as LOGO, which has 2 steps, right? The first step of LOGO is known as policy improvement, where we use rewards from the environment to improve our policy. But since we work in sparse reward environment, this might not be enough. And in order to guide our policy, we do the policy guidance step, where we try to find out a new policy around a trust region of the policy suggested in the policy improvement step towards the behavior data or the behavior policy. Right? And we also showed that it works theoretically. And then now next, we want to move on to how do we implement LOGO, or how is LOGO implemented, and what are the challenges that come with implementing LOGO. So that's what we're going to do next. So let's talk about the implementation of LOGO. So the policy improvement step can be implemented using the normal TRPO framework, and I'd strongly recommend people reading the TRPO paper, which essentially talks about implementing this particular algorithm. But how do we implement the policy guidance step? Like, this is our objective that we want to implement, and we know that theoretically doing so will provide us policy improvement, but how do we actually implement this? Right? What are the challenges that come with implementing this objective? Firstly, if you notice that we have a dpi-kl here, which essentially means that this requires sampling from the current policy that's being executed, which is hard to do. So the objective is, can we come up with like a surrogate objective to this objective function where optimizing the surrogate objective is equivalent to optimizing this objective function mentioned here. Second, this objective also requires the exact knowledge of the policy pi-b. Can we estimate using samples from policy pi-b, because sometimes you might not have access to the behavior policy, but rather data from the behavior policy? Can we estimate this objective using samples from the behavior policy? So our goal right now is to develop an approximation to the policy guidance step, which is amenable to sample-based learning. So solving this objective is hard. It's hard because you need to sample the current policy that's being optimized, and you need the knowledge of the behavior policy. How do we address these 2 challenges? So that's the current goal. So what do we do? So in our work, we basically model the policy guidance step as another reinforcement learning problem, but with a different reward function. So we basically show that try to show that like the minimizing the KL between policy pi and pi-b can be solved as a reinforcement learning problem with a policy dependent reward function. Right? So suppose we define a reward function or a cost function cpi to be the log of policy phi of s comma a divided by policy pi-b. We can similarly define j, that's basically the infinite horizon discounted reward, j, the value v, the q function, as well as the advantage function. And we can show that solving the reinforcement learning problem by essentially minimizing this quantity j is akin to minimizing dpi-kl. Why is that? This can be seen using this very simple lemma, and I can go over this, this proof. It's pretty simple. So suppose we define our reward as follows. We can essentially write down what j of c pi looks like. And it basically comes down to replacing this c pi with the log of pi by pi-b. And this immediately turns out to be the average KL between policy pi and pi-b, where the average is taken according to policy pi. Right? So what we have essentially shown is that you can solve the KL, you can solve the minimization of the KL between policy pi and pi-b by solving it as a reinforcement learning problem with a policy dependent cost function, where the cost function is essentially the log of pi by pi-b. Right? There are some certain challenges associated with defining this policy dependent cost function, but I'll come to those in a bit. So what do we have? Right? So we have the policy guidance step, which is defined as follows. And what we do is that we replace this policy guidance step using a surrogate objective. Right? Similar to what TRPO does, we can also kind of write a surrogate objective, but we must take into consideration that that you're dealing with policy dependent cost functions as opposed to policy independent cost functions. But the proof goes through, and I've omitted the derivation for this presentation because it gets a little complicated, and I want to like stay away from that and provide you a big picture, but I'd be happy to go over the derivation either during the chat session, or you could read the paper for this. Right. So if you notice, what we have essentially done is that we have modified the policy guidance step to be another step of TRPO, right? To be another step of TRPO, but with a different reward function, where the reward function is this policy-dependent reward function or cost function, right? So again, there's another challenge here. The challenge being this cost function that we defined here, again, has the policy pi b coming in, right? Which means that we still require the knowledge of policy pi b. So how do we eliminate this? So we do this by basically training a discriminator using the demonstration data and data generated by the policy pi k plus of to estimate the cost function c pi k plus of. So it can be shown that if you write down the proof, if you write down the expression for a discriminator, it essentially comes down to this particular scenario. And again, the details of which I'm omitting, but you can take a look at our paper to see how we do that. So what does this kind of tell us? So this tells us that logo can be implemented by taking advantage of any TRPO code base, because it simply comes down to doing two steps of TRPO. The first step of TRPO with the rewards from the environment, and the second step of TRPO using this policy-dependent cost function. So that's good. So now what's the another advantage of our algorithm is that it can extend to a situation where we have incomplete observations, which is very pertinent to real-world applications. Okay? So how do we handle these incomplete observations? Right? For example, in many situations, we may have data which can be collected in a lower dimensional state space, but we want to train an algorithm in a higher dimensional state space. So what does this mean? So let's say we are trying to solve a problem where of obstacle avoidance problem of a mobile robot, where we have a mobile robot and we wanted to avoid an obstacle and then reach a goal point, right? But we have data collected just for reaching the goal point, let's say, right? So if you notice that the data collected used for reaching the goal point does not include any sensor information to sense the obstacle in place, right? But the task that we're trying to solve is that we want to sense the obstacle in place and then reach our goal. Right? So can we use the data which has been used to solve the navigation problem to aid learning of avoiding an obstacle, right? Because you have to avoid an obstacle and reach the goal point. So you kind of, can you distill the information of reaching the goal point from the first task and use it as a guidance to solve the obstacle avoidance problem? So that's the overarching question that we're trying to answer. And we can show that, yes, we can do that using our model, because the behavior policy only appears through the policy-dependent reward function. And we can just project the state space into a lower dimension and we can solve this. So essentially, even if we have data, let's say from like a lower dimensional problem, we can kind of use it for a guidance for a higher dimensional problem. So that's what we're trying to say. What essentially happens is that your reward function is modified as follows, where you have log pi of s comma a, where pi tilde b is basically consists of the projected version of the state space. So what are the results that we have? So we first show the results of logo on Mujoko environments, where Mujoko are these physics simulator environments on different tasks such as walker, hopper, half cheetah, and inverted double pendulum. And we see that our algorithm basically outperforms all of the baselines except in one case. And we also show the performance of logo even in the partial information scenario, where our demonstration data only consists of a subset of the true state space. So we also show the performance of logo on a turtlebot experiment for obstacle avoidance. So how do we do this? So the goal here is to train an agent to reach the goal by avoiding an obstacle, right? So what are our state space? Our state space is essentially the relative x, the relative y, the orientation to the goal, the relative orientation to the goal, and the 2D LiDAR scan of the bot. What's our action? Our action is essentially the linear and angular velocities. And we have the following sparse reward structure, where you get +1 if you reach the goal, -1 if you collide with the obstacle, 0 otherwise, right? So what's our guidance policy or the behavior policy? So we obtain a behavior policy using a low fidelity kinematic simulator only for waypoint tracking. That is, we take like a simple differential drive model, and then we train a reinforcement learning algorithm to track waypoint, right? This tracking of waypoint happens without any obstacle in place. Notice that this behavior policy does not take in any LiDAR information or anything, right? But what this behavior policy possesses is that it possesses crucial information on how to track waypoints. So can we use this to guide the learning of an obstacle avoidance problem? And what we do is that we take this behavior policy and we train on Gazebo, where LiDAR data is available to avoid obstacle avoidance. And we show that our algorithm is able to reach the goal by avoiding an actual obstacle. So for example, if you see logo, it's able to avoid the obstacle and reach the goal. The behavior policy has no knowledge of the obstacle because it does not have LiDAR data, so it directly goes and collides with the obstacle. And another algorithm, such as TRPO, fails to learn because it's a sparse reward environment. And yeah, I have a video for this. So initially, we show that we can also do waypoint tracking, where our bot is able to attain waypoints marked in blue and reach the target marked in red. So this experiment, again, I've skipped over because of the constraint of time, but this is also one that we show. And in addition to this, we also show that we are able to avoid an obstacle and reach the waypoint marked in blue. So what's the TLDR of this first half of the talk? Learning in sparse reward environments is hard. Designing reward functions is hard, right? So suboptimal demonstration data can help aid the learning process. So suppose you don't have access to well-defined reward functions, but you have access to demonstration data. You can kind of use this demonstration data to help aid the learning process. So what we come up with is we come up with Logo, which has 2 steps. The first step is the policy improvement step, which uses rewards from the environment for improvement. And the second is the policy guidance step, which tries to find a policy in a trust region around the policy suggested by the policy improvement step towards the behavior policy/data. And our algorithm can be extended to the incomplete observation setting as well. How am I on time, Nathan?
I think maybe we can like start the discussions soon. If you're like
yeah. So in any case, give me like a minute or so. I'll just quickly go through. Right. So another problem is that suppose you're given a set of structurally similar sparse reward environments. Training using the algorithm mentioned in the previous would require us to train for each of these environments, which would require millions of training samples. Right. So can we exploit the fact that the environments are structurally similar, and then can we use demonstration data to collect only a few samples from an environment and then learn in that environment pretty quickly or adapt to that environment pretty quickly? So this is where our other work which comes in, which is basically extending the same sparse reward approach to the meta learning setting, which I'll kind of, I think it'll take a while. So I'll just skip over this and we can move to the discussion part, if that will be okay. Yeah.
Thanks, Desik. Your talk was super interesting, and I'd recommend you all to check out the other talk as well. Sorry that we ran out of time, unfortunately.
No worries. Yeah.
Right. But yeah, so if you have a question, please go ahead and speak up. You can like turn on your mic and just ask Desik. But if you, for some reason, are not able to do that, you can put your question on the chat and we'll be happy to read it out for you as well. Desik, do you see the question? Would you like me to read it for you or from the chat?
I can see. So I think you can unmute yourself and ask so that it'll be easier, if that's fine. The theoretical guarantee that Logo will eventually enforce pure demonstration-free RL, and so it should find optimal policy is clear. But do you see any problem for that becoming true in practice? For example, AlphaGo was trained into where Okay. But do you see any problem for that becoming true in practice? For example, AlphaGo. Yeah, so I think you've understood, like the first part is clear that the theoretical guarantees that Logo will eventually um, enforce pure demonstration free RL, and so it should find the optimal policy is clear. Yeah, that's true. But do you see any problems for that becoming true in practice? Well, yes, that does become true in practice because essentially what you want is that, at least in sparse reward environments, you want your RL algorithm to try to obtain dense rewards from the environment and try to obtain some sort of rewards from the environment so that it can use that to optimize the learning process. And this demonstration data kind of acts as a guidance to obtain that that reward function, that rewards from the environment, essentially. So we are not exactly doing what AlphaGo does, where you train completely using demonstrations and then fine tune using RL, but rather we intertwine both the using the data as well as tuning with RL in like one step. So we provide one step of guidance and one step of one step of RL improvement. So in our experiments in Logo, if I can quickly move back, we actually try to compare it with the exact scenario that you mentioned. So if you look at this example, which is known as BC-TRPO, here we basically warm start with the demonstration data and then do like an RL algorithm. And it can be seen that in all of our examples that performs pretty bad, right? The reason being that we do not have a lot of demonstration data, and that's something which I didn't mention. We just have like very few samples of demonstration data. So just, starting off with pure demonstration and then fine tuning is not going to help. And you said that AlphaGo was demolished by a thing which was trained only from self-play, no additional human knowledge. Yes, that is true, but that's again with like dense rewards, and it won't work in sparse reward environments. And as you can see, like just pure TRPO just doesn't work. It's performing pretty bad. Yeah, I can take more questions.
Okay, if there's no other question, I actually want to ask one. Yeah, so in the Logo update step, I see you're like moving towards the BC direction, but you're sampling your rewards from the policy, right? Have you?
What do you mean towards the BC direction?
Like, can you go to the the figure you had before the intuition of Logo?
Yeah, I can. Yeah.
Yes. So, like the policy improvement happens in the direction of the. Wait, I'm sorry. The policy guidance happens towards the behavior policy, and the policy improvement is like a TRP update based on whatever you have right now, right?
Correct.
So
Yeah.
what would happen if you like swap those two? Like you train, I think, is that what the BC TRPO does? Like you
No, so
use
BC TRPO warm starts. You just warm start with BC,
right,
and then you do TRPO after that.
okay, right. But
So
what if you do like policy improvement in the direction of the behavior policy, but like
policy
guidance?
improvement will not happen in the direction of behavior policy, right? Because policy improvement happens using the true rewards from the environment. So it will happen towards PyStar.
Okay, right, got it.
Yeah.
Okay. Are there more questions?
Yes, one question.
Yeah.
In the policy guidance step, do we actually use any kind of reward in that formula, or do we only?
No, so the policy guidance step does not use. So yeah, the policy guidance step, it is formulated using a reward function, which is a policy dependent reward function. So if I can just, yeah. So this is the policy guidance step objective, right? This is the objective that you're trying to solve. So we say that this objective can be solved as follows. Suppose you define your own reward function, which is like a policy dependent reward function. This is not the reward function coming from the environment, but rather you design this reward function to be a policy dependent reward function where C pi is log of pi comma pi divided by pi b. Then when you define your, when you solve a reinforcement learning problem using this reward function, it is the same as minimizing the scale objective.
But wouldn't this lead to a problem if you have like demonstration data that is to one part of higher quality and to one part of lower quality? So some demonstration data that is already pretty good, and other demonstration data that is very bad at following the environment's rewards. Then
so you're saying that suppose you have a mixture of so correct. So as long as this assumption is satisfied, where we say that, like, you know, overall, if it's able to provide some sort of benefit, if the behavior policy is able to provide some sort of benefit, we'll still be good.
But would you say this whole approach is suited to a mixed demonstration set?
So in practice, no. I mean, if you have a lot of mixed demonstration data, even, you know, like running some sort of let's say pure imitation learning algorithms. Let's say you have like a mixture of bad data and good data. Just running pure imitation learning algorithms also will not work because you have this like multimodal kind of scenario.
Sure.
Yeah. So here, yes, we kind of assume that we have data coming from like a single behavior policy. If you take our approach here, sorry for the constant. Yeah. So we just say that we have a single behavior policy that generated this data. We do not consider the situation of mixed, but I don't think it'll work well with mixed. If we have like very starkly different behavior data mixed in like a policy bucket, it's not going to work. You'll need some sort of filtering to, you know, choose the best behavior data and then, you know, train using that, if that makes sense.
Yeah. Thank you.
Yeah. So we actually have like a follow-up work which is under review where we kind of address this whole idea of like learning with like different levels of expertise data in like a federated scenario. So yeah.
Okay.
Yeah. But that's a good question. Thank you.
We are almost out of time, but I think we can take one more question. Maybe someone has, or we can wrap up right after. Are there more questions? Okay, I think that seems to be it. Desik, could you stop sharing?
Yeah.
Okay, awesome. Yeah, thank you all for joining today, and thanks, Desik, for your presentation. It was
Thank
very
you so much.
insightful to hear about you. And we also have like more sessions coming up in the future. In a couple of weeks from now, we have Professor Brad Hayes joining from CU Boulder to talk about multimodal planning and communication for HRI that is safe and collaborative. And I hope to see you all the next time. And thanks again for